I wrote this summary probably 2 classes ago. I posted it in 2 places of that day's notes, as an introduction and as a conclusion. It explains to you, it's supposed to explain to you why we're talking about light when we were talking about atoms. Why are we talking about light? Well, if you follow the progression, so from Dalton's model of the atom, which is basically a cue ball and a pool table, to J.J. Thomson's model, which was chocolate chip cookie model, negatives in there, positives outside, to, that was Thomson's. Looks like an English muffin, Thomson English muffin, right? Rutherford's, which had the positive there and the negative here, to Bohr, which had positive and several places that the negatives could be. The reason why we're talking about light, I said this before, I'm going to say it again in case you didn't hear. The hydrogen atom is like a little piece of machinery. The hydrogen atom is probably the simplest machine in the universe. It consists of a proton being circled by 1 negative electron. Therefore, it only has 1 moving part, which makes it a very simple and beneficial target to ask ourselves, what does it look like? How does its structure explain what we see about hydrogen? With only 1 moving part, but 5 colors of light coming out of it. When you energize hydrogen, when you put hydrogen in a tube and run electricity through it, it glows purple. You take that glowing purple light and pass it through a prism, it separates into 5 unique individual colors. Those colors don't change. It stays the same. And you've only got 1 moving part, the electron, that's attracted to a nucleus, a positive nucleus, a negative electron attracted to a positive nucleus, and therefore it possesses potential energy. That potential energy, by attraction to the nucleus, a change in that potential energy is the only way that you can get energy out in the form of light. So when hydrogen glows with 5 different colors of light, that means that electron is falling to 5 different positions. That has to be. There's no other way to get energy out of that. Now, there might be, but this was one of the clearest aspects. So that's why we study light. We study light in chemistry because it is that light that indicates to us how the electron is moving inside the hydrogen atom. And that becomes the basis for us understanding all other atomic structures. So Bohr was the one that came up with this model of the atom, that the electron is sitting on an orbit and it can fall 1, 2, or from here 3 places. So you add another orbit. Now all of a sudden I think you have 6, because you can fall. You have those 3 falls, plus you have 5, 6, 7. Okay, so 7 falls. So by adding by having 4 rings around the hydrogen atom with its 1 moving electron, and having that 1 electron fall from 1 ring to the other rings, you can explain all the 5 colors of light, plus predict other colors of light that you can't see in the ultraviolet and infrared. They look for them. He was right. They're there. His model of the atom seems to work. Now, I'm going to bring up a couple more things about Bohr's model of the atom. Not only does Bohr's model of the atom explain where light comes from, and I'm going to say this very clearly.
Mister, for ultraviolet and the ultraviolet will be the one with the most energy, and then the infrared will be the one with
the least energy.
Okay.
Yeah.
Mister.
Yes.
So if hydrogen only has 1 atom, wouldn't it be, 1 electron, wouldn't it only be on the first electron level? How is it falling down?
That's where it should be. That's where it should be. But when you put hydrogen in a glass tube and run other electrons through it, a beam of electrons, as they pass through the hydrogen gas, they make the hydrogens shake. They're colliding with the hydrogens. They're colliding with the other electrons that are already in orbit around the hydrogen, and they shake them. They impart energy. Just like if you run through a crowded room, you will make the people that you encounter shake. You'll hit them, and they'll fall. They'll lose their balance. They'll bang into other people. You will be imparting your energy to that group of people as you run through the crowd. And that's what these cathode ray tubes do. They shoot electrons across, and as those electrons fly through the low pressure, very sparsely populated, but it's there, but not much. It allows the electrons to pass through, but as they pass, they bump or jostle the hydrogen atoms or whatever gas you have in there, which then causes their electron to go from the lowest, which is called the ground state orbit, they get promoted to a higher level, and that's when they start falling.
So the light is from when it goes up, and then when it's falling back down is when the light comes?
Yes. You don't get light from raising electrons. I'm going to talk about that in a minute. You don't get light from the electron going up. You get light from the electron falling. All light comes from falling electrons. I used to give this as an extra credit question in my honors chemistry class. Notice I put an asterisk. I stopped doing it because it became so laborious. I would get hundreds of emails. What about fireflies? What about meteorites? You know, and I have to answer them. No. Or if I didn't answer them, they come, I sent you an email first. Nope, that's because you were wrong. I would give extra credit for anybody that can find there are two exceptions to this. There are two exceptions to where light comes from other than falling electrons. But I'm going to tell you, at this level of your life and education, you probably will never know the other two sources of light. Isn't that sad? The teacher's telling you you're never going to know something. You won't hear it from me, kids. There are at least two other sources of light that are really bizarre. And maybe having introduced it like this, I'm motivating you to look it up to prove me wrong. And if that's the case, great, we'll learn something. But the majority of people, the majority of knowledge that most people have about light, the majority of experience, most of us will never, ever see the two exceptions of light that do not come from electrons falling. Candlelight, laser light, meteors passing through the sky, starlight, laser light, sunlight, firefly light, bioluminescence in the ocean light. It's all electrons falling from having been excited in the atom. When the electron is up here, we call this excited. When it's up, because it's got potential energy. If you think about this as a ladder, the higher up the ladder you climb, the more energy you have. We call that the excited state. Down here, we call this the ground state. And it kind of means exactly what it sounds like. If this is a ladder, the rung that's closest to the ground is called the ground state. That's the lowest energy rung of the ladder. And the electrons are being pulled down, and that's why they fall. So all light comes from falling electrons. I have said that in class before. Whether you caught it or not, I don't know. I'm trying to make it very clear right now. If I make that a quiz question or an exam question, I'm going to have multiple choice. Where's all, which one of these is not the result of falling electrons? And I'll have something like lasers, fireflies, meteorites, and then probably one of the answers will be none of the above, or none of the above. All light comes from falling electrons. So you need to know that. It's important. That's one of those little facts that you ought to know. Light comes from electrons in atoms falling. Now, sometimes the electron gets so much energy when it gets smacked by another electron or something like that, that it actually gets enough energy to leave the atom. And we call that plasma. That's what flames are. It's actually the glow inside the fluorescent lights. That's a plasma. The electrons are actually escaped from the nucleus, escaped from the atom, but they still fall back. They're attracted. It's like if you watched Sandra Bullock in the movie, was it Gravity? Was Sandra Bullock in a movie called Gravity? I think so. Great space movie. If you like science fiction, it's not that much of a science fiction movie. I mean, it's like science fact movie. She's a shuttle pilot. They're up working on some satellite or something, maybe the Hubble, I don't know. And then all of a sudden, the space shuttle passes through a debris field of a satellite that was hit by something. If you've ever stuck your head out the window of a car or ridden a motorcycle and hit a bee or something, it hurts. A bug, it just, it hurts. Well, that bee's not moving very fast. You are. Well, when you're moving 20,000 miles an hour and you hit something, it's going to hurt. It's a good movie. Why am I talking about this? Why am I talking about this? Science movie. Gravity. Oh, because what you shoot up in the air must come down. What goes up must come down. Well, we found out that's not exactly true. If you shoot something up far enough, Voyager 2 will never come back to Earth. It's leaving the solar system at this point. But many things that we have shot up into the air, satellites, you would think they would stay in orbit long enough, but they eventually fall back down because even though they're 200, 300, 400, 500, 1,000 miles up, there's still a little bit of atmospheric resistance. And over great periods of time, they do lose their speed and fall back to the Earth. So I'm really off on a rabbit trail here. We're talking about electrons. Electrons fall down to the thing that is pulling them, which is the nucleus. For some reason, they stop at the first energy level. We're going to come back to that statement shortly. That's a big problem, but we'll talk about it in a minute. So light comes from these electrons falling. The distance that they fall is what determines the color. A short change in energy, this change right here, change in energy, is described by the equation H times frequency. In other words, if you measure this distance and plug it in for your change of energy and solve, you will get the color of light out. And here you might find that this is infrared, IR. And if you fell from, here to here, maybe you find out that that's red light. And if you fell down here, maybe that's blue light, The distance that you fall is a specific amount of potential energy, and it determines the color light coming out. Now let me say this, in reverse. In reverse. When there's an electron in a ground state, I'm putting it down there now, it's the same idea though. If something were to hit this atom, whether it be light or another electron, and the amount of energy, h nu, or the amount of energy here, 1/2 mv squared, if the amount of energy, this is particle energy, this is wave energy, if the amount of energy was exactly equal to that jump in energy there, or this jump in energy here, if that equaled that amount of energy, then the electron would absorb it and jump to the next level and become excited. If the amount of energy that was offered either by the electron or by the wave of light, if that energy did not equal that gap, then it would not be absorbed. It would pass right through it. There's nothing to absorb it. The electron in the ground state would say, sorry, can't use you. Wrong denominator.
It would just stay the same?
It would stay the same. And this, by the way, is why water is colorless. Light is passing through it, but in the visible spectrum, Roy G. Biddulph, there are no electron jumps possible in the water molecules that correspond to the energy possessed by red, orange, yellow, green, blue, indigo, or violet. And so that light passes right through and we don't see anything. Now, if you had eyes like an insect, I've heard, I don't know, but I've heard that insects can see some infrared and some can see ultraviolet. You would find that water has color. Water does absorb in the infrared. And if you had the ability to detect that, you would see that water has color. You'd be like looking at Gatorade or something like that. Gatorade has chemical dye in it that will absorb particular colors of light. That means the dye molecules in Gatorade have electron transitions. They have rungs of the ladder that are matching exactly the colors of light that will then get removed, leaving the orange light, leaving some red, leaving some yellow. The Roy part of the spectrum passes right through, and you see that. What you don't see is the light that's being absorbed by the orange Gatorade, the green, the blue, the indigo, the violet. That light is being absorbed and converted to vibrational energy. So that's what I'm trying to say here. Not only do atoms emit energy, release energy in the form of light when the electron falls, but electrons can start in the low ground state. And if the energy of the particle or the wave coming in, it has to match exactly the jump. It can't be part of it. It can't be more than it. It's got to match.
What if it's higher?
Same thing. If it's higher, maybe it'll match another transition that's more. But if it doesn't match any transition in that atom, then the atom will reject it. The electron cannot absorb that energy.
So if it matches, it's going to go up. And then instead of keeping that energy, it just releases it with light and goes back down to like its base.
Well, that's where I'm going to talk to you right now. It has a couple options. When the electron gets excited, let's do this one. When this electron, here comes a light wave, and this energy, h nu here, equals, let's say this band right here. This is delta E, change in energy from low to high. If that equals that energy of this light, then this absorbs that light and it goes to a higher energy state. Now, there's a couple things that can happen to an electron in Bohr's model of the atom once it has absorbed that energy. There's about 3 things that can happen. One of the most common things that happens when electrons absorb energy, the electron cloud starts to vibrate, pulsate with the increased energy. And as it pulsates, it bangs physically, it bangs into other atoms around it, and you have converted radiant energy into vibrational energy, and we would say that the thing is heating up. It's getting hotter. You go out and you touch a black car on a summer day, and you'll say, "Ooh, it's hot, don't sit on it." Because black absorbs all colors, right? Many colors. Which means whatever dye or pigment they put in the paint has many, many electron transitions available so that it's able to remove all 7 Roy G. Biv colors out of the visible spectrum so it looks dark to us. All right? And so one of the things that an excited electron can do to the atom is it begins to vibrate. And by passing the energy off as kinetic energy, the electron can go back down to the ground state, having lost its energy as kinetic or vibrational energy.
Where does the energy go, though?
Well, it has to be passed on by contact with another atom. If there's not another atom there that it can smack into, then it can't. You know.
The other atom basically just takes its energy.
Yes. So and I'll get to you in a second or two. So all of the atoms that are in this, that are all in this metal structure here, they're all in contact with each other. So when one absorbs a photon of light and it causes the electron to get elevated in energy, and it passes that energy on in vibration, those atoms are next to each other. So when the electron cloud starts vibrating, it causes the ones next to it to also vibrate, to repel away. So they move back and then they move forth again, back and forth, back and forth. And you've lost your energy from radiant energy to kinetic energy, and you say, wow, this thing's warming up, it's heating up.
So the same process just after one happens, it just starts happening in other atoms too?
Yes. So if you're shining a broad swath of light on an object, and the many trillions of atoms are absorbing radiant energy and converting it to vibrational energy. And you're saying, wow, the thing is getting hotter. It's just warming up.
What happens when there's no more atoms for it to bump into? Like it's bumped into all of them.
Say that again, please.
Like when it ripples through all of them, what do you do with all that energy?
Well, the whole thing starts pulsating and vibrating. Now, we kind of addressed this earlier in the year, I think. At some point, if they're continuing to absorb energy and converting it to vibrational energy, at some point, the vibrations become so violent that they overwhelm the inter-atom attraction, and you go from being a solid to what? What?
A liquid?
Yes, a liquid. So at some point, if you continue to absorb energy so that it overwhelms the interparticle forces, you're vibrating so violently that it tears them apart, you're going to a phase change. You're going from solid to liquid. And now you have more than vibrational energy. Now all of a sudden you have translational energy, where you're zipping from point A to point B. You have rotational energy, where you're tumbling. So you have many other modes of dumping energy then, storing energy. And if you continue to absorb energy, then you break those liquid attractive forces and you go to the gas phase, where you completely escape each other and you're now zipping around as a gas. Now, that's one way that an energized electron can get rid of its energy. It can set the atom into vibration. Another way it can do it, if the electron jumps up and it immediately can re-emit that light, then we would call that reflection, if it's immediate. If it absorbs the light and immediately re-emits it, there's actually a geometry to it, the way it happens, that produces a geometric equation for angle of incidence, angle of reflection. If the electron immediately absorbs, when it absorbs the light, if it can immediately re-emit it in the same wavelength, we would call that reflection. And there would be no energy imparted to the atom. It gained and lost, gained and lost, gained and lost, and just keeps doing that. There is a situation, however, where it absorbs the energy. Now listen to this. It could absorb the energy, get promoted up, emit a portion of that energy, maybe a small portion, so it comes out as red light. So that means it still has energy. and that turns into vibration. So you can get a combination. But the total energy of the light emitted and the vibration has to add up to whatever the light was that it absorbed. So if it absorbs a blue light wave, it could get rid of a red light wave if there's a place to land. There's got to be a place to land. So if it was here and it absorbed blue, and then it dropped down to here by emitting red, and now you still got an energized electron, that energy could be lost through vibration. So sometimes you get a combination.
What determines what happens?
It's the structure of the atom, the wavelength of light that's absorbed, and what phase of matter the atom's in, whether it's in a molecule or whether it's in a pure substance. What else? How many energy levels are available? Whether or not the material has the ability to vibrate.
What you said about how it could only absorb the energy if it's like an exact amount, does that still apply to like the vibrational part aspect of it too?
Yes, because here's the thing. No matter what kind of energy you're talking about, it's quantized. Energy comes in bundles. So that also means that only certain vibrational modes are possible. Only certain vibrational frequencies are possible. So the atom has to be able to vibrate at a certain frequency or it will not vibrate. If you give the electron a certain amount of energy and it wants to get rid of that energy, but for whatever reason that atom can't vibrate at that frequency, then it won't do that. It won't get rid of it as light or, that's, somebody asked, what determines that? And that's partly that. Energy is quantized. It doesn't matter whether you're talking about radiant energy, E equals h nu, or whether you're talking about motion energy. It's got to have, it comes in bundles. They're very small bundles, so it looks like if you have a group of them that it looks kind of smooth, like continuous, but it's still bundles. And so when an atom wants to lose energy, when the electron is high up in energy, it can lose it by either emitting a photon of light of a particular frequency that matches the jump down, or it can cause the atom to vibrate at a certain frequency. And what's going to determine that frequency is its mass and its size and shape. Well, shape is pretty much spherical, but mass and size are going to determine its vibrational modes.
So when it's vibrating, if it's losing energy, doesn't it have to fall levels, which means it's also letting out light?
Well, no, the electron will fall by causing the atom to vibrate at a certain frequency. And that's where Bohr's model fails us. We're trying to see the electron falling again. When it converts its energy to vibrational energy, believe it or not, here's the really wild thing. The electron just ceases to exist at that level, and it reappears magically at the lower level. And that's why that was one of the problems with Bohr's model of the atom. The electron does not pass through the region of space between two orbits. And if you look at my notes, that's one of the complaints about Bohr's model. Where does the electron go between orbits?
How does that even work?
It doesn't work if you're talking about particles. If you go stare at your swimming pool and ask yourself where the waves go in between waves, then you start getting a field. And that's all you get is a field. It's not even knowledge. It's not like a knowing. It's just a feeling. When you watch waves and a wave will pop up here and then it'll pop up over there, and you didn't see it go in between there. There's a lot going on about the transmission of energy between particles that we can't see. All we can see is the effect. But wave behavior is far different from particle behavior. We're going to get more into that. Let me bring us back. Let me reel us back in and just say this. I said there were like 3 ways that the energized electron can give up energy. Number 1, vibrationally. And yeah, we talked, you guys are the first people that got that out of me today, but we're talking like high level, college level chemistry. When we start talking about vibrational modes, that's like graduate level chemistry. You calculate the vibrational modes of atoms. But that is a true conclusion that you get that. If you get that vibrational energy is also quantized, it has to match. The energy that the electron gives up has to match the ability of the atom to vibrate at that frequency. Then you're way out there. That's good stuff. It can give it up by vibration. It can give it up by falling. And if it falls the exact distance that it rose, and it does it instantaneously, we call that reflection. And you can think about that. There's a difference between reflection and a few other functions. Why do mirrors reflect light? There you go. You're getting somewhere there if you read up on that. But again, that's high level physics and chemistry. So you can give up energy by re-emitting the light. You can give up energy by vibrating. You can do a combination of the two. You can give up a lower energy light and cause the balance to turn into vibrational energy. And that's typically what happens. It's probably more common that it does that. And then there's one more phenomenon that you're very aware of, but you probably didn't know. Some things, most things when they absorb energy, they either convert it to vibrational or some combination of vibrational and immediate re-emission of a photon of energy. And we would call that reflection. But there are some things that we know of that absorb the photon of energy and they don't give it up immediately. They give it up later. And that's called, ready? Glow in the dark. Why do your toys glow in the dark? Why do the little stars on your ceiling glow in the dark? Because, and you know how to charge them. You know how to make a glow in the dark thing. You have to hold it up to light, right? Otherwise, it's no good. So you hold it up to a bright light, turn off the light, and it's glowing. Look, it's glowing. Why are you holding it up to light? You're storing energy in the electrons of that material. And usually it looks green because there's a particular material that has the green energy band that releases it slow. I think it's a phosphorescent material or something like that. The fluorescent. I'll have to check that out. Anyway, you charge up a glow in the dark thing by holding it up to a light. You're storing energy. Photons of light are hitting those electrons. They're causing them to go up into high energy modes. You turn off the light, and then you're actually watching those electrons slowly fall. Now, some of the energy is lost to heat, vibrations, but the other energy is given off as green light, greenish light. There's a band that the electrons are falling that is equivalent pretty much to green light, greenish light. So there you go, something to think about.
And then just to make sure for the second thing that could happen, when it absorbs the energy and then it lets go of the light that like comes down as a color of light and lets down another light, that it can like switch, right?
Let me see if I understand. You're saying you absorb a photon of light, the electron gets energized, it falls back down, it can give off a different color light. Is that what you mean when you say switch?
Yeah, like when it falls and it falls the same amount, it's giving off one light, but it can also give off another color of light, right?
Right. So if you have this atom, and here comes, let's say this is green light. And here's this electron. And this jump right here just happens to equal from here to here. This delta energy is equal to green. How do you know what that is? H nu, where nu would be, let's see, red is 700. Here you could do, if you could think of this, 700, this is like 400. So this is like 650, 600, 550, 500, 450. How's that? Pretty easy, right? Every 50, roughly. It's not exact, but it's close. So green is 550. So lambda is 550 nanometers. Since C equals lambda nu equals C over lambda. So we could say that this energy is equal to H times C divided by 550 times 10 to the minus 9 meters. When you calculate it, you get units of energy. All right, I'm not asking you to do that right now. I mean, you should be able to, but I'm not asking you right now. I'm just pointing out, if this green light has energy equal to Planck's constant times speed of light divided by 550 times 10 to the minus 9, and that's equivalent to this jump, then this electron will absorb that energy. It will go up here. And now, once it's up there, it can either immediately fall back and give off that green light, which we would then call reflection, or maybe it falls here. And let's say it gives off yellow light. Well, yellow light is less energetic than green light. So there's still a little bit of energy left in this atom by the electron being up there. So maybe that energy turns into vibration. And like I said, the electron's not really falling and slowly rising. It disappears from where it was and reappears where it will be. It vibrates and then poof, it's gone, and then poof, it's here. It's like teleportation.
Okay, so when the hydrogen, you know how you said when it does the side that lets out the light to get out energy, and it's a purple light.
Yeah.
The other colors the 5 other colors that it lets out, is that from like the separate energy levels that fall?
The 4 other colors refer to other transitions that are possible. So if you have the hydrogen, I'll draw 4 rings, 1, 2, 3, 4. So you have an electron that falls all the way down, that's going to be more purplish light. When the electron falls a little bit of the way down, that's going to be more blue. Maybe that's the red. And then, you've got another transition from here to here, So each one of those falls represents a different color of light because each one is going to be a different distance. And if you look at the book or anybody online, if you look at somebody's good drawing of a Bohr model of the atom, the orbits start off far apart, close to the nucleus, and as you go out, they get closer and closer together. And there's really no two gaps that are the same. So there's no two colors that are the same. You know, different jumps are going to give different colors. All right. Okay. Now I'm going to take this back. There was something else I wanted to say, but we got to get on. We're moving, and you can ask questions. I like it. I like when you ask questions. That's good. But so Bohr's model of the atom, I drew 4 rings, and it produces 7 colors of light. I believe the visible. If you look up the visible colors of light that hydrogen gives off, they are not from the outermost. They're from I think it's from the second ring to the other rings. They produce visible, and all the way to the first ring is where you start getting your ultraviolet. So, in Bohr's model of the atom, see if I can draw this. So you can see as you go out, the rings get closer and closer together. And if you remember from math class, there's something called asymptote. Do you guys remember that word, asymptote?
I remember it, but I don't really remember what it means.
In a graph, if a graph has a curve, but the curve begins to level out.
It's like a little line.
Yeah, and this never reaches that, but it approaches it closer and closer and closer. They call this the asymptote. Okay, well, what happens is as you continue to add rings around hydrogen, they get closer and closer together. They reach an asymptote of a radius of 53 picometers, which turns out experimentally to be the width of hydrogen. You can actually measure the width of atoms. There are things we can do. We'll do a lab coming up soon. We'll do a lab with tinfoil where we will approximate the size of an aluminum atom. It's not tinfoil, it's aluminum foil. There are ways that you can calculate the width of atoms. So
Is that asymptote like the max energy that it could have?
Yes, it is. And what happens is if you promote this electron anywhere here, it's still in the atom. Once you give that electron enough energy to go beyond 53 picometers, it's now considered to be escaped, and you have now ionized the hydrogen atom, or any atom, whichever atom you're talking about. If you pump in more energy than the band between that atom's, that electron starting point and the radius of the atom, once you've done that, you have now given the electron enough energy to totally escape the pull of the nucleus, and it's considered to be ionized. Now, it can do random collisions and whatnot. It can be bumped back like a pinball. If you come back, and once it gets close enough again, it will feel the attraction. And once that happens, it will then fall. And when that happens, it will give up that energy as light, which is what's going on in our fluorescent tubes above our heads right now. The fluorescent lights above our heads are filled with a gas that the stream of electrons is just bombarding, knocking its electrons loose, producing a plasma, which is a charged gas. And then the electrons are perpetually being, as long as the light's on, they're perpetually being recaptured and releasing energy, light energy. So going back to what I was going to say about, I believe it's the transition from these guys to the second ring that accounts for visible light, and to the first ring is where you get your UV light. That's a really big energy band there. So any electrons that are falling there are going to be giving off ultraviolet light. And it was this model that Bohr produced that would account for the visible colors of light that then led to the predictions that ultraviolet light existed. They produced the detectors. They verified, yes, he's right. There's 5, actually 10, because there were 5 ultraviolet and I believe 5 infrared colors of light that no one had ever observed of hydrogen. And boom, there it is. Hydrogen, Bohr's model of hydrogen predicted something that nobody anticipated, and therefore he's given the Nobel Prize. Parentheses. I said this in 2 of my other classes now because I noticed in the epic rap battles, people were saying stuff like, Chadwick received the Nobel Peace Prize. And I want to clarify something for you so you don't sound ignorant in the future. There are, I believe, 6 Nobel Prizes, one of which is a peace prize. There's Nobel Prize in Chemistry, Nobel Prize in Physics, Nobel Prize in Literature, Nobel Prize in Economics, Nobel Prize in Medicine, and Nobel Prize in Peace. So the Peace Prize is just one Nobel Prize. And the story that I know from what I've read, and I haven't studied it in depth, I think I read a Wikipedia article on it one time. Alfred Nobel, Nobel, became ultra rich in Europe because he took a Chinese invention called gunpowder and packaged it in a little stick form called dynamite. And he invented dynamite from the Chinese gunpowder invention to help farmers turn their forested fields into farmland, plowable farmland. If you've got a bunch of stumps, you can go out and harvest the trees and turn it into construction material, wood and lumber, but you still got these stumps and roots in the ground and you can't drill, that you can't till, you can't plow. So Alfred Nobel figured out a way to use gunpowder to blow up these stumps out of the ground. And once you blew up your stump out of the ground, you could drag it off with a horse and cart and or ox cart. You could drag it off, and now you have the ability to plow your field. So he thought he was contributing something for the good of humankind, and a good heart. But what happened was, obviously, somebody figured out if you took that stick of dynamite and taped it or attached it or tied it to an arrow, you could launch it into a ship, into a fort, or into an army and wreak havoc. It was a better way to fight a war, basically, for whoever had it. And so his sales went through the roof. He became immensely rich, but he also became consumed by guilt that he had made the world a worse place. On his deathbed, he had a will that basically says, all of my savings, all of my money, I want it put into a trust fund. Don't touch the trust fund, but every year take the interest off that trust and award it to the people in the world that have made the most contributions for the betterment of humanity in the fields of chemistry, physics, literature, economics, medicine, or outright peace, kind of bring warring nations to peace. So that's the story behind Nobel Prizes. And depending on the exchange rate and the economy of the world, it could be $500,000 in American, it could be up to $1 million, depending on whatever. So that's what Bohr won. Bohr probably, I don't know if it's physics or chemistry, probably physics. We're really going to a section of chemistry that is really more about physics than it is anything else. Chemistry involves the change in the outermost electrons called valence electrons. That's chemistry, true chemistry. Physics is pretty much about the nucleus. I don't know why, but that's the way it is. I do know why, but not for now. So Bohr's model predicted these colors of light, ultraviolet and infrared, that nobody else had anticipated. And we got a little bird friend. There's a bird in my window squeaking at us. Yes, hello.
I could hear it. I was like, what is that?
And he's hopping up on the ledge. He's literally looking in at us like, what are these people doing in here? Anyway, the big issue with Bohr's model of the atom occurred when he got his prize and somebody said to him, hey, Bohr, I love what you did with that hydrogen atom, and I was really hoping you could help me because I just don't understand how to apply it to helium. And Bohr's probably like, I'm fictionalizing right now. I'm sure he said something like, yeah, I'll get right back with you. Problem is, nobody else, including Bohr, could ever adapt his mathematics, his equations, to produce similar results that would match the atom, the element with its spectrum. And if you look up either at my notes or right here, this poster, there's a picture of this in my notes today. You can see that every element has its own very distinct pattern of light that it gives off. And that's because every element has a very distinct structure of orbits. You can imagine in thallium, that doesn't mean there's only one electron or that it can only move to one place. It simply means that with thallium, all the other transitions available to its electron are outside the Roy-G-Biv range, outside our visible light range. So I'm going to say hello to the bird. I want to say hi to the bird. He's being our friend. You want to go to school, Mr. Bird? There's no screen. We could let him in. Then you'd have to deal with, what do you do? He's gone. All right. So, Bohr's model and its equations, you could visualize it as being applicable to helium and any other atom, but none of the data could produce anything like hydrogen's data did, where you could take the 5 visible light bands of hydrogen and then draw a picture that would then predict 10 invisible colors of light. You can't do that with the others. It doesn't work. It doesn't predict anything real. So the only conclusion is really, Bohr got really lucky somehow. He got the answer, and the answer are the colors of light. He worked backwards, and he made up a picture that, very fortunately, maybe I don't, maybe it's not fortunate, but it predicted coincidentally, I guess. It's beyond coincidence. It's not a coincidence. There's no way that his model could predict to the nanometer the wavelengths of light that he did. But it just doesn't work for helium. Once they got frustrated with trying to adapt Bohr's model to any other element, it was like you've heard of cracks in the armor. That's a cliche, an idiom. It had cracks in the armor. Once they perceived that Bohr's model was not what they thought it was, the answer, I don't think they can revoke Nobel Prizes. Where's the money, Bohr? I've spent it. People began expressing some other doubts. Like, here we go. Here's another big question. We're just going to draw two orbits. If the electron is falling because it's attracted to the nucleus, that's the mechanism. Why doesn't it fall all the way into the nucleus? Why isn't everything just a bunch of neutrons? Why doesn't the electron fall into the nucleus, cancel the proton, and turn into a neutron? Why is that not happening?
Isn't it because, like you said before, like things don't, like you don't touch things because they can't get super close to each other?
Well, that answers why the electrons on our fingertips don't touch the electrons on the tabletop or other fingertips. They push against each other. It does not answer what about electrons that want to be attracted to protons? Why do they stop? I mean, it makes sense if you've got electrons on the outside of all your atoms, why they don't come into contact with each other, because they're pushing away according to the inverse square law. The closer they get, every time you half their distance, you quadruple their resistance. It doesn't explain why a negative could not unite with a positive. They want to. And I did, when you started asking me, isn't it because, I thought you were going to refer to something I said the other day. I did say something the other day about neutrons decaying. And when a neutron decays, it breaks apart into a proton, an electron, and a third particle. I believe it's called a muon. I haven't studied this in a long time. And in order for the proton and the electron to rejoin, there does have to be that third particle present, or it won't go. But they didn't know that then. They were looking at this as a classical, and when I say classical, there's a technical definition of the word classical in science. It refers to the Newton laws, the Newtonian, Isaac Newton's laws of motion. Force equals ma. For every action, there's an equal and opposite reaction. There's a series of equations based on Newton's discoveries. And that's classical. So when they were looking at this, they were looking at this as a classical particle. That's like a planet. That's like the sun. If the planet is falling towards the sun, why does it stop suddenly? There can't be any structure holding it up. Because what would that structure be made out of? Are you proposing now there's yet more particles? And how would we observe them? I mean, what are they? So there was that issue. There's another issue. Same line. Let's see if I can do this. Why can't the electron just fall a little bit? It's just say, I don't feel like falling the rest of the way. I'm just going to stop here for now. I'll give off some infrared light. Not much, low energy light. And I'll pause here for the day. I don't want to go any further. Why can't the electron just keep gradually bumping its way down, losing its energy by slowly giving up infrared? Why does it have to go from here to here? In other words, why do elements have distinct spectrum?
Because energy comes in bundles.
Yes, it does. And apparently there's a minimum amount of energy or some multiple of a minimum amount of energy equal to that's not there. But if you remember, look at this model out here on the outside, towards the outside surface, those orbitals are getting closer and closer and closer together, and they're getting closer and closer to the size of h, because h times 1. If nu equals 1, if it's 1 per second, then you would have that energy band would be equal to 1 Planck unit of energy. These are getting closer and closer together. So this is still bigger than hundreds of thousands of units of Planck energy. So it doesn't quite explain. So you're right, energy does come in bundles, but remember, towards the outside surface of the atom, we begin to see the orbitals getting closer and closer to 1 unit of energy apart. and this is probably hundreds of thousands of units of energy apart. This gap is 100,000, I'm guessing. But let's say that gap is 100,000 bundles of energy wide. So that is a true statement, but it's not explaining why the electron can't fall one bundle of energy and stop there. So it's a related question, why the electron doesn't fall to the nucleus and why it doesn't fall step by step by step and stop along the way. And I appreciate the suggestion, but like Bohr and his contemporaries, we will continue to be frustrated if we continue to look at the electron as a particle and try to answer the question that way. Somebody else is going to think out of the box in a moment. I'm going to introduce you to somebody else in a moment. But before I do, let's look at.
Wait, so we know the answer to this, you just haven't told us yet?
That's correct.
Okay, I was thinking that it just hasn't been solved yet. I was like, oh, okay.
Oh, well, there's lots of problems that haven't been solved yet related to that. So don't give up. If this interests you, you can certainly study it and you know, make some contribution to our understanding of the atom.
Would that be looking at the atom as like waves, how waves work instead of a particle?
Absolutely, absolutely. And that's what they're doing now with these new quantum computers. The electrons are no longer being looked at as a particle that's present or absent. Present is a 1, absence is 0. Now they're using wave entanglement of electrons to produce values, which makes, you know, an electron many, many more times more informational than just whether it's present or absent. So you could certainly get a career in quantum computer development, and it's all about wave mechanics. It's all about quantum mechanics.
So the explanation to this would be the when they send the electrons through the like Dr. Quantum in the Dr. Quantum video.
Yeah, I'm just now going to draw that. But I've got a series of videos that talk about waves. And if you watch it without my explanation, you're going to be wondering, you know, what is Beightols got all these wave-related videos for? But when I try to weave them together into my view of the atom, I hope it makes sense. I think it does. And I think when you realize, when we look at the electron as a wave, it all of a sudden becomes a no-brainer. You're all of a sudden like, what was the big mystery? Of course, that's the answer. Well, the mystery then is actually, to me, the mystery is not why certain orbitals, and when we start talking about them as waves, we're talking about it as orbitals rather than particles have orbits, waves have orbitals. And we start talking about waves with orbitals, you got to say, I think, if you understand, you're like, there's no other answer. That's obvious now. But then what the real question for me becomes is, well, what's waving? If electrons are waves, what is waving? Right? But let's not go there yet. I told you I would get there when we talk about Heisenberg. And Heisenberg's coming up in the conversation today. So we're getting close. So if you haven't watched, I told my other periods this, and I think I insulted somebody second period. If you haven't watched the Dr. Quantum video or the other videos that I'm linking, but really, you got to watch the Dr. Quantum video. If you haven't watched it, I'm going to say it the opposite way of how I said it in second period. You're not approaching this class in the most intelligent way possible. That's opposite of what I said in first. I basically said you're being dumb. You know, it's like, hey, take it easy. All right. But, you know, if you watch the Dr. Quantum video, you know what I'm talking about. That makes it so clear why we think the electrons are now waves. All right. So I'm going to draw my electron gun. It's just like a cathode ray tube. And over here, I've got the positive screen. So this is negative. This is positive. And I put a slit in my screen. This is a metal plate. It's positive charge. But I put a slit in it. And behind that, I'm going to put some photographic film. If you're like, this is really lame, Beightols, well, then watch the Dr. Quantum video. And now you turn it on, and it begins shooting electrons like bullets. Here's what you get. You get an image of the slit. Profound, right? No, it's not profound. It's exactly what you would expect. It's so obvious, it's putting melody to sleep. So there's nothing spectacular about that until you add a second slit. You're like, oh, let's see what happens if we put a second slit. You do not get this. You do not get this. No, you don't get an image of two slits. You get something more bizarre. What you get is something that looks like this. And I put an image of this in notes where I actually produced this pattern using a laser in my classroom 2 or 3 years ago. I shot it through double slits formed by bending a paper clip on itself, stuck in a roll of tape, probably that exact same roll, and put the image on that wall over there, put the laser over here, and we got this image, and it's in my notes, you can see it, but that's light. And it was Christian Huygens 300 years ago that explained that light was a wave because of this. But electrons do this too. This is called an interference pattern. It's called an interference pattern. And the explanation is, if you have two sources of waves, and you can Google this on YouTube, or you can YouTube it on YouTube, wave interference patterns. And there's people with little wading pools and pitchforks that are vibrating, and it produces this. And there's a guy, Veratium or something, whatever it is. He's got a show, Veratium or Veratium, and he does this on a palm, and he produces interference patterns. It's a great video. It might be linked to mine. I don't know. So if you get a source of two waves, two sources of waves, rather, not a source of two waves. That's one source of waves. And then this is a source of waves. And you look, there's a pattern of interference where they cross. The peak of one wave, the peak of this set of waves meets the peak of this set of waves. And when they strike, well, that's over here, and over here it's 4. But there's a band, there's a band. I don't know, I didn't do a good job, but there should be a band there. In other words, you get these peak intensities that pile into the plate over here, pile into the plate here, pile into the plate here. In other words, you get stripes. Two sources of waves side by side will produce waves that add up constructive interference wise and produce stripes of intensity bands, whether it be a seawall, a beach, a photographic film. And this was the interpretation of the electrons. They do this. It was an experiment done. A guy named deBroglie said, we have been thinking of the electron all along. We've been thinking of it long. Bohr's model of the atom does not answer all the questions. It just opens a door. Bohr's model of the atom, it's wrong. What he got right was that he employed the concept of energy in bundles. That is right. We still teach Bohr's model of the atom for this reason. I'm going to tell you why. Because for classical electronic equipment, it still works. For lasers, LED lights, computers, old-fashioned computers that we use right now, it still works. It works great. Microwave ovens works great. Bohr's model of the atom is to the truth of the atom as your bank statement is to the truth of where your money really is. If you don't know what I mean, you've got a bank account, maybe grandma gave you some money for Christmas or your birthday, or, and some people have given you some money. So you put a bank account and you put your money in the bank account. Maybe you have $700. Maybe you have $1,700. I don't know. Every month you get a statement from the bank saying how much money you have. It tells you how much money you took out from the ATM machine. It tells you how much money you deposited. It tells you how much money you earned in interest if you have interest. It tells you how many fees you had to pay for having the bank account. If you go knock on the door of the bank and say, excuse me, my name's Harry Potter. I want to see my money. I believe you have it in a cave guarded by a troll. They will laugh at you because your money is not in that bank anymore. The minute you put money, the minute you walk in and hand them an envelope of cash and a deposit slip, you turn your back. You're going to give your money to the next person in line and say, I'd like to withdraw $500, please. And you say, oh, yeah, sure, here. Your money's gone. And if it's not gone in the next transaction, by lunchtime, an armored truck shows up at the back of the bank and they pile your money in there and they send it somewhere else because it's not safe to keep it in the bank. But you get a piece of paper that says it is in the bank. And when you go to the ATM, it acts like it's in the bank and it works. Everything works. The whole banking system is working based on a lie, or at least not on a clear statement of truth. But it works. And Bohr's model of the atom is just like that. The electrons are not in those little circles, but they act like they are. And it all works as long as we're doing classical electronics and chemistry. We're starting to understand now that when we're starting to look at individual atoms, individual molecules, and individual reactions, instead of statistical averages, we're starting to see mysterious stuff. Okay, and it's more quantum weirdness than classical. All right, so I got to finish up here. I won't even have time. deBroglie won $1 million, not the Peace Prize, because he realized that there wasn't much difference between an electron and a photon of light. Photons of light come from electrons. They're both dimensionless. Neither one has a radius. Electrons don't have a radius. Can't measure the width of an electron. The electron is almost massless. For all intents and purposes, it is massless. To 20 significant figures, the mass. Okay, we'll just leave it at that. There's a lot of similarities. So deBroglie said maybe the energy of a particle, called the electron, is equal to the energy of that same thing as a wave. And if so, you can set these two equal to each other.